and my presentation is about writing performant C++ code. And I'm going to take you through a little bit of information that'll help you write better C++ code by breaking some assumptions that people have. I optimize code for a living, and I have to have my head filled with trivia about machine-specific features, assembly language, and the bits and bytes that most people don't need to know about. And what I'm trying to do with this presentation is bring you a set of actionable information that you can use to write better code and give your compiler a better chance at creating efficient output. And so here's a little bit about me, and you can visit my blog and my website to learn more. But I generally end up doing the similar work for all different clients on embedded, on server, on PC, on mobile. It's all variations on a theme, and that tends to be that people who are writing very complex math and abstract kind of projects are not really concerned with the specifics of their target machine and trust the compiler to just magically create great output. And compilers have come a long way over the last few years, but you still need to at least help them along the way and provide some hints to allow them to write better output for your programs. And that's what I mean by having empathy for your C compiler, is that understand that the compiler can only work with what you provide it, and that it's really not that great at knowing what's happening when your code is running. All it knows is what statically your code looks like at compile time, but you have more knowledge of the data that you're going to be feeding through your program than the compiler does. It doesn't know the values of your variables at runtime unless they're constants. So that's one of the things that we're going to talk about, is providing more details where it's important for the compiler and how you can help it in its job. The first topic here is about the cost of your choices. So each line of code in C++ is definitely not equivalent to another. So something simple like an assignment A equals B plus C will turn into at most 2 instructions, but typically just 1. And then something like memcopy is a function call to a who knows how many instructions. Usually it's at least 100 instructions just to check boundaries and check memory alignment and lengths and so forth. So the compiler is smart about doing constant checks at compile time. So if you tell it to copy 4 bytes like that statement below, it's smart enough to not even call memcopy. It'll just do a move instruction of 32 bits. But if you have a variable at runtime, the compiler can't know the size of the data in that variable, and so it's going to take the slow path. So this brings us to, what does the compiler know? So information that you provide it in your code, in your class definitions, tends to focus more on runtime values. So is something a constant? The compiler can know that that value can't change, and so it can make better choices for generating code. Again, like in the last panel, if I call memcopy with 3 variables that are different, that are any value at runtime, versus telling it a constant value of a length, it will generate very different code. So with that knowledge, it could avoid making that function call at all. All right. And one of the other topics that some of you might not appreciate being called out is the slowness of object-oriented programming. So the passing of objects to manage your data is definitely a good thing. I'm not criticizing that, but what it entails is now you've got these independent memory objects that are passed by pointer to different methods, and then the methods act on the member variables through that pointer, indirectly through that pointer, and it leads to a couple of problems. And one of the problems is that the compiler can't know the volatility of those member variables, meaning if your method modifies a member variable, the compiler cannot make an assumption about the rest of your program. Even if it's single-threaded, it can't necessarily know if other code cares at that instant that your member variable has changed. And so it treats it as volatile. So if you change the value of a member variable, it will constantly write the new value through indirectly through the pointer, dereference the pointer, which is much slower on a PC than having a local variable in a register. And so we'll talk about ways coming up and how you can make that situation better if you know you're going to modify member variables frequently. So in this example here, I call it the slow way. You can see in the left that my function takes a object pointer called myStuff and a pointer to data and does a simple sum of all the elements in that data pointer. Now you can see that it's modifying the member variable called sum in the loop while it's doing that. And if you look at the output that generates with Compiler Explorer, you can see that it's having to write back the new value of the sum variable into the structure every time it's changed. So you can see that it's adding the input data, and then it's storing that new value of the sum, and then it's adding another value of the input data, and so forth. It's grouping them, it's doing some loop unrolling, but it's not able to do this efficiently because each time you're reading and writing data from memory like this, memory is much slower than the processor, and so you're incurring a heavy cost by doing it this way. Now, a better way of doing that loop is going to be creating a local variable that has the work done on it. So I have a local variable called local sum, and that will take the sum of all the input data, and then at the very end we write that value into the member variable of the structure. And what that generates is much more efficient code where it's able to hold the sum value in a register and not have to write it back to memory each time. And then at the very end it gets written back into memory. And so this turns out to be a much more efficient way to do it on modern PCs and mobile. And one of the things that I have to know a lot of detail about, and hopefully you don't, is about your target machine. But some details are useful to know about your target machine. For example, is there a great speed disparity between memory and instructions? So on modern PCs you have a 2-3 gigahertz Intel processor. The CPU executes instructions much faster than the memory can read and write data, and so you have a bottleneck if you're processing a lot of data. And so there are different mechanisms to try to improve that situation, such as a cache and special regions of memory that are faster. So that's one of the things to consider in how you accomplish your task with the PC is the memory slowing you down. Other things to think about are the instruction set architecture. Do you have hardware floating point instructions, and are you using floating point math? Do you have single instruction multiple data instructions or not? Do you have a hardware divider, which is really a recent invention in CPUs, and other special instructions that are usually accessible by intrinsics? So some of these can save considerable work, like for example the pop count instruction counts the number of 1 bits in a variable, and the way to do that in C is just to loop over each bit of your variable, which is incredibly slow, versus the pop count instruction, which can do it in 1 clock cycle. And then there's the issue of, are you running on a protected mode operating system like Linux or Windows or OS X, or are you running a bare metal kind of system like embedded? And that can make a big difference in I/O and system calls. So let's talk about the memory. So embedded CPUs, like your typical Arduino kind of controllers, typically have static RAM and flash memory on the chip that are the same speed as the CPU, and so there's no real extra cost to reading and writing data from memory. They don't have a cache mechanism because it's not necessary. But on your typical PC or mobile device, the dynamic RAM is much slower, in fact up to 200 times slower than the CPU is running, and so you really want to avoid mashing data in and out of the memory, or just accessing a variable over and over through a pointer like we saw above, because even in the cache it's not too quick. Something else to think about is the use of malloc and free and new and delete, in that in a PC where you have a limited amount of high-speed cache memory, the PC is constantly trying to free blocks from the cache that are no longer needed. And when you use malloc and free or new and delete, the operating system typically marks that memory as evict from the cache because you've told it that you don't need it anymore. And then if you go back and allocate even the same size data and it's the same physical memory, it will have to reload it from dynamic RAM into the cache. And so that operation of dynamic structures, especially in a frequently used method, is very expensive in time because of the memory delay. So you always want to place your working data set in the fastest memory or fit it in the cache if you possibly can. So this brings us to, is it really possible to write C++ code that's knowledgeable about its target platform and yet still portable? And I say that it is, because you can still make use of this knowledge in how you sparingly use memory and treat things as if memory is slow. That kind of operation won't hurt you on any system. But for truly target aware, there may be some special instructions that you have to make use of that are only available on ARM or only available on Intel. And in that case, group your code such that all the common code can be compiled to all systems, and then there's a small portion of your code that is very specific to your target, and you can if-def it or use specializations in your class to contain that code that's different on each system. But when I do that in my projects, I always keep the original C++ generic version as well, and that way it's much easier to test that my optimized ones aren't broken and to see what the algorithm is doing without having to walk through some target specific code. And I always encourage the use of intrinsics and SIMD if you want to get the most out of your PC, your program, and I'll cover that in the next few slides. So then math operations are something that I notice this a lot with mathematicians when they write code, is that they don't pay attention to any of the expense of the operations that they're using. And division and modulus are always expensive to do, even when you have hardware divide. And so there are ways of avoiding using division. Something simple that I use sometimes, if we're going to be always dividing, for example, a variable by a constant, if you're always dividing something by 3, instead it's actually faster to have a constant of 1/3 and multiply it. It sounds silly and it sounds intuitive, but the division operation is always going to be much slower. Another thing that I see in a lot of code that I optimize is this sort of carelessness with type conversions between floating point and integers. And it is always expensive to convert between floats and ints and back, at least as expensive as doing the operation you're doing. So for example, if you're just multiplying an integer times a float, that may take 1 clock cycle, but there's an extra clock cycle wasted in converting between a float and int, and you may have it converting back to an int when it's finished. So there's sort of a hidden cost to all that. And so always take care when specifying your variable types because of that expense. Another thing to think about is the standard C library. It contains a bunch of math functions that are actually double precision floating point, which can take a lot longer to execute, even if your machine has the hardware support for double precision floating point. 64 bits of precision are not always necessary, and you should consider using 32-bit versions of those functions, which have a suffix of f in the name. So for example, the square root becomes square root f for the excuse me, single precision version. And of course, lookup tables are still a useful tool for avoiding things depending on the precision that you need. Some operations, arctangent, exponentiation, those are extremely expensive, and if you can use a lookup table and get the same results, use the lookup table. Something else I mentioned earlier was about system calls. And so on a protected operating system like Linux or Windows or OS X, the operating system internals are run in a higher privilege than the user program. And calling between the user program to the operating system involves an extra delay if you're moving data back and forth. So something as innocuous as file I/O, like fwrite, fread, are very expensive per call. And so something innocuous like the code on the left, which reads an array of integers one at a time from a file, will be much, much slower than something like on the right, where you read the entire array in one shot. So if you can group your file access and network access into as few calls as possible, you'll get tremendous speed. Something else to think about is memory. If you're using a lot of memory and small bits all over the place, it can be much more efficient to manage your own buffers and just pre-allocate a memory pool and don't keep freeing it and just use it over and over in your code. The same thing with thread pools. It's the same idea. So I mentioned earlier about SIMD, which stands for single instruction multiple data, and all that means is a single instruction executed on the CPU can do many things in parallel. And what it can do, it can multiply 8 floating point values in one shot. It can add them, it can subtract them, all the standard kind of operations, but wider. So you do things in parallel. So the CPU typically has very wide internal registers, between 128 and 512 bits wide. So if you have a 128-bit internal register and you're working with 32-bit ints, you can work on 4 at a time. And generally the operation that you're doing must be identical to all 4, all 8, or all 16 of the elements in the register. So what can it get you? Well, you can get considerably more work done in the same amount of time and energy on that machine, as long as you can put your work into conveniently grouped groupings that are not different. So if you can do the same operation on all the elements, you can get a lot of speed out of SIMDs. Things that helps with typically are pixels or sound data or something where everything is treated identically. And if you don't make use of them, you're really wasting a lot of potential on your PC that you're going slow and you don't have to. Now there are compiler options that have to be turned on to enable them, because over the past few years the instruction sets have been changing. Intel every couple of years releases a new version of their SIMD instruction set, and not all processors support them, but we're at a point now where any modern PC, it has at least a certain level of support for SIMD, and every mobile device as well. And so you need to generally turn on an option in your compiler flags to enable it to generate those instructions. That brings us to auto-vectorization. So auto-vectorization just means that the compiler, when asked to, will turn your code into efficient SIMD instructions. It'll group your data into vectors of 4, 8, or 16 elements so that they can be done in parallel. And that sounds wonderful, and it does a decent job for most things, but it's limited in what it can accomplish, because again, it's looking at your code not with a brain, but with a simple logic state machine. And so some things it handles well, but it'll give up if there's any complication in the code. So what we can do is help it along with giving it some hints and understanding when it's not going to be able to do anything. So here's a simple example where SIMD will be used by the Auto-Vectorizer pretty easily. We have a simple loop which does a sum of elements that are all identical and just returns the sum. And so if we look at the output of the compiler, we can see that it is grouping this into groups of 8 of 4. So it's looping over, sorry, it's grouping in groups of 8 elements over two SIMD instructions. So it's reading 2 sets of 4, expanding them, adding them, and unpacking them and adding them to the sum and storing them again. So At the very end, at the tail here, this is typical, so after it tries to do 8 elements at a time, whatever's left over, it does one at a time. Now we can help it generate much more efficient code if we give it a little hint, and that is, if we put another loop inside our main loop that basically tells it it's safe to use groupings of this constant amount. In this case, I told it 32, so this vector grouping variable here is a constant of value 32. So now I'm telling the compiler that I know that I've got groups of at least 32 of these elements in a row that are safe to read and write. The code that it generates does basically what we told it, that it's working with much larger groups and using more internal registers. And so this turns out to be much more efficient, because by telling it can work with 32 at a time, it can load them all into registers, work purely in registers, and then store them back. And this is much quicker as far as memory, as far as making use of registers and so forth. So this is a very typical trick to get the vectorizer to generate better code, and that is to tell it with another inner loop inside your main loop that it's safe to work on groups this large of your data. And then again, like the compiler is doing earlier, for any odd-sized values that are, say for instance we have 33 elements, so there'll be once through this loop and then another once through here to pick up that last one. Now we've come to what happens when the Auto-Vectorizer doesn't do so well. So in this loop we're doing a sum of the product of these two arrays, but only if the value of the A element is greater than or equal to 0. Now this causes the compiler to give up, because we've told it that we can work with large groups of vectors 16 at a time, and we're doing a simple operation which is the sum of this product. But with this conditional statement in here, typical Auto-Vectorizer just gives up. The thing that's interesting about this is that the instruction set does support doing this in SIMD without a branch. There are comparison and masking kind of operations that can make this work with a straight through kind of SIMD that will be much more efficient, but the compiler doesn't try. It's beyond the level of what a compiler can do to turn this into vector code. So in that case, I would recommend writing your own SIMD code. It's not that complicated. So here are the challenges working with SIMD. So a lot of software never bothers to enable them because it takes extra effort, or in that case you have to do a little extra work with intrinsics to get the computer to do what you want. Your algorithm also needs to allow operations to occur in parallel. So imaging and pixels are usually good candidates, but not everything fits the SIMD model. So for instance, if you're working with vector triplets, you've got X, Y, and Z that you're doing. Depending on how you lay it out, the compiler may not even try to do vectorization of it, because it's in groups of 3, not in groups of 4, and it's not necessarily going to read and write 3 elements at a time, because the hardware of the computer is designed to write and read powers of 2, so it doesn't fit. And as we saw, compilers are not great at creating SIMD automatically, and you may need to explicitly write those instructions. Now the compiler has a set of what's called intrinsics, which are C-like representations of those instructions, and it's really not that hard to use. It is more to learn, but it's not that complicated. The complication comes that each platform has its own unique SIMD instructions and multiple revisions of them. So for Intel, there's SSE, SSE2, SSE3, 4, AVX, AVX2, and that causes extra work on the part of the programmer to have to test if that capability is there, has to write a special version of the code for that, and so forth. So it adds quite a bit to the complexity, but if you need speed, that's what you're going to have to do. And as I said before, if your data doesn't fit neatly into the SIMD register size, you can still sometimes make use of SIMD with a little bit of creative thinking, but the compiler generally will not do it for you. So now we're down to the very last slide, leaving you with a few things to remember that'll help sum up what I've gone over. So, rules of the road. The thing that I really want you to come away with is the one I've marked in red here, which is to test every assumption. That's the main killer of performance on software, is that the programmer is burdened with knowing a million little bits of information and has to make a bunch of assumptions in order to get any work done. You have to have a working set of knowledge in your head in order to write code without having to keep going back and looking things up and confirming them. And many of those assumptions turn out to be wrong. And so you'll write your algorithm and you know for certain that something is true or something is going to work this way, but did you really test it? Did you really know that it is? And the other thing to think about is the data that you pass through your algorithm. Knowing the nature of your data can be helpful in choosing the shortest path for the most frequent kind of data. So if you're working with data compression, something like arithmetic coding, you have the most probable symbol and the least probable symbol, and so the code path for the most probable symbol should be the shortest code path because it's the most probable symbol. And so by making its code more efficient and taking care of the exceptions on the longer code path, you can make it go faster. So that's it for this presentation. Please feel free to write if you have any questions, and you can see a lot of my strange and crazy experiments with microcontrollers and performance on my blog and my Twitter feed. And thank you for listening.